Alrighty. Let me try to check one last thing before we begin. If I have the right version of the questions or not. Okay. Alright, I think it's time to begin. Alright, just for the sake of simplicity, I know you guys have trouble with other questions and like a bunch of them are easy. So I'm gonna make sure I cover them in a sequence because, just people can follow along if they want to watch the recording. I know you guys are smart. You guys came in early to kind of work it out, but most of the people probably do not have time. That's why they're not here to join us today. But the thing is, like, the homework's gonna be due on Saturday. A lot of people are gonna start to panic during the end, and I don't like that. Okay, when you panic, you don't really learn. It's like you just want to get done with it. So when the due date approaches, you just want to have the green over there on the Webwork and nothing else. So I would say that's the worst part to learn. And yeah, if you make a video in like a good following order, it will be easy for them to remember and walk across it, right? So that's the idea of moving in a sequence. So let's keep them in our mind, people who are going to be watching this later, and then begin the session, right? So Webwork 7 has to do with trig sub / trig integrals. Okay, and if you were here on the Tuesday session, the one where we discussed the trig sub, the concept of it, right? It would be very easy to follow along. It should be just the thing. And then today as well, I'm gonna focus on the method more than explaining the method, right? Because we segregated these two sessions and talking about the theory on Tuesday, giving you an option or attempt or an opportunity to try yourself till today. And then after you're done, we can go over that together today. So that's what the motive is today, right? So if you need help understanding completely what's going on, I would highly recommend watching the Tuesday session. Okay, the recording of that is posted in the Discord as well, and I'll post it again just in case if you need it, right? So let's begin. The first question for me is 120 x to the 5 secant squared x to the 6 dx, right? So on the side note, you need to remember this integral is a classic u sub integral. Okay, the reason is because the integral of secant squared x is tan x, right? And you also know that if you want to substitute x to the 6 as u, then you use 6x to the 5. You need that thing with the dx in order to carry the substitution. Okay, so we have both of them. I'm gonna write this 120 into, I guess, 6 times 20. Okay, nothing fancy. I just made it look like easy to substitute. And now when you do a substitution, this integral because you make this u, this all of that becomes a du. So you have that integral, which evaluates to be 20 tan u plus c, and then whatever the value of u is, you plug it back in. And that's how you finish the first one. Any questions about this method? Or like this particular question? Not really, right? Very straightforward. Easy peasy u sub. And that was probably the only easy u sub here in this particular homework. Alright, so let's go to the next one, where you have question number 2. Talking about tan 12x. So for this integral, I need to keep in mind that if I plug in u as tan x, then I need to have a secant squared x dx to carry on that identity, right? And then the other thing I want to know is that could be written as tan squared x plus 1. So these two things are important in order to start off this integral, right? So I'm going to write it this way. I'm going to strip off two of these and make a facilitator right here. Okay. So what happened to the 120 in the beginning in the first question? The 120 got split up in 20 times 6. Right? And that's just my way of doing it. You can do it the other way too. Awesome. So we got this. The facilitator is there. I can write, because of this identity, I can write secant to the power of 4 x as secant squared x whole squared, which happens to be this. So then now my integral only has tans in there, because that's the whole motive of having a substitution here. Plus 1 whole squared. This should be tan squared x, my bad, times tan to the 12x secant squared x dx. So now if you make these guys u, right, just a tan as u, you know the secant squared x dx will become du. So this integral in the substitution world becomes like this. U squared plus 1 whole square times u to the 12 du. Move on to the next page. So question 2, the steps here, is to make sure you have secant and tan like this. You need to know all of the stuff in order to begin this integral. Okay, the first thing you need to know is if you substitute u as tan, you will have secant squared x dx as du. Right, so you need to have a secant squared x there to help you facilitate a substitution if you plan to do so. Then secant squared x also can be written as tan squared x plus 1, so you remember how to convert a secant into a tan, so that you can reduce every other secant you see into tan and substitute them all. That's important. And in this particular case, you have secant to the 4, which could be written as secant squared whole squared, which could be written as tan squared x plus 1 whole square, right? So with that being said, we've kind of like made our question into this format and then start ahead with our substitution. Does that make sense? All right, we're going to move on. So now here, if you expand this, well, that's u squared plus 1, so it should be u to the 4 14 plus u to the 12 du. And this is 13 divided by 13 plus c. And hence the u that you would have is just going to turn out to be plus c. And that's how you solve the second question. Makes sense, right? Not too bad. The question that's question number 3, I covered that in our tutorial. Question number 3 last time we covered up was here on a Tuesday session. So I talk about the motivation here that once you have that integral, the tan to the 5 secant to the 5 dx, that's what I have. If you wanted to go by substituting, if you want to substitute tan as u, then you need to have a secant squared x dx there to facilitate the input, right? So when you do that, you would have to strip off two of these guys and write it on the side. So at tan phi is u, secant cube, and secant squared x will become your du, right? So when you do that, in this particular case, this secant cube cannot be converted into any tans, because you can only convert and use that identity for even powers of secant, right? Like this identity to convert a secant into a tan would only need an even power. So when an odd power happens here, that tells you you cannot do this substitution. So that's why in red it's not going to work. So we have to go the other way, right? The other option is to substitute secant as u. So if you want to substitute secant as u, then if you remember, the derivative of secant is secant x tan x. You need to have a secant x tan x dx to help you facilitate that system. So what you're going to do is you're going to strip off one tan, one secant, combine with the dx to make that facilitator. And now you can convert the remainder of tan x to the power 4, write it as tan squared of squared, and because tan squared x could be written as secant squared x minus 1, you have now everything converted into an integral of secant squareds, right? And then you substitute as u, so you would be able to get to that result very easily. So this integral I'm going to carry on from here. So now this could be written as that's how it turns out to be. Expand the integral. And when you plug it back in, you get secant plus c. Pretty much the same approach with this question too, right? Does that make sense? Awesome. Move on to the questions that are actually troubling people, right? So that's question number 4 for you guys, right? In this case, what I want to do is I want to give you the fact that when you have a square root and a quadratic, you want to complete the squares. That's the step. So you got to complete the squares, you got to do a trig sub, simplify, then show. Okay. This could be assumed to be a semicircle too, but this would be a semicircle if it's in a numerator, right? The function itself is not denoting a semicircle in this particular case, because it's in the denominator, right? So we're gonna start to like think about it that way. Plus, That would be very beneficial to understand if this was a definite integral, but this is not a definite integral, right? So we don't really know how big that semicircle is, right? We're not kind of like figuring out the area under the curve. We're just finding a general antiderivative. So keeping that in mind, I do the simplifications in this way, okay? So when you want to complete the square, in this case, it's already in a completed square form, okay? So you don't really need to do anything, because a completed square form, as I discussed in our session on Tuesday, is already given in some constant, which is going to be a x plus some b whole squared plus c. This could be written like that already, because this could be written as negative 81 times x minus plus 0 whole squared plus 64, right? As long as the quadratic does not have any x terms, it's already completely square. Like, we'll see some examples where we have to complete squares, so we'll see that. Right now I have this. So what I'm going to do, though, is probably not going to talk about the motivation behind it, but I'm just going to follow the method, okay? If you need to know the motivation, you have to check out the recording that I did before. That was on Tuesday, right? Because then it will be super long. I want to keep the session short one, so that we just focus on questions, get it done, right? So here, I would want to take this and write it like this. So try to follow along the algebra. It's not too bad, just a little tricky, okay? So I took out a 64. I combined that 9x and the 81 and 64 and x squared under the same whole square. There's nothing special that I did there, right? Now, which could be written as the 64 can hop out of the square root. Could be 8 like this. Now, because of what we discussed, I know it would make my life so much easier if this thing was cos of t. So I'm going to do my substitution here. I'm going to say 9x over 8 equals to cos of t. So x equals to 8 over 9 cos of t, and dx will just be 8 over 9. Derivative of cos is minus sine. So dt. So I have everything ready for the substitution, right? Let's see, before we go to the integral world, let's see how this simplifies to be something nice. So after substitution, this will come. Which could be written as sine squared of t, which essentially is just sine t. So after the substitution, the simplification step, we're reaching this point, right? This has been simplified all the way to 8 sine t, okay? So now I'm going to bring it back into the integral. The integral was 1 over all of that, so it will be 1 over 8 sine of t. The dx has now been changed into this. That's what you're left with. And that's probably the toughest integral out there. That reduced to be negative 1 over t plus c. Now you have to substitute back for t. So you have to go back to this relationship. T is equals to cos inverse 9x by 8. So that will be your final answer here. Plus c. And that's how you do question 4. Now, wasn't too bad. Assuming that you know that you have to do it this way and do it this way, you know, assuming that you know that you have to substitute for cos, it wasn't that bad either, right? The motivation here could be developed by practice or like looking at other similar examples, but that's gonna take time because you're doing it for the first time, right? That's why I want you to try your homework for yourself first. Not because I've already grounded it, you know, so you kind of already know that this is where you're getting stuck, and now you know how to get out of that too. That was question 4, right? We can move on to the next one then.
Hey, can I ask a question about question 4?
Absolutely, yes.
Thanks. So I didn't really understand the step where you went from minus 81 x plus 0 squared plus 64,
That
and you
was like
substituted
from here,
that
right?
into the, yeah.
Yeah. The reason why I showed that here was to say the first step you want to do when you see a quadratic inside a square root is to do a completing squares. Okay? And then this particular example has already been given in a completed square form. So I showed it this way to show you that this is in a completed square form, and you can carry forward your simplification and trig substitution after that, right? So there was nothing that was supposed to happen here. I was just trying to show you that this is already in a completed square form.
Ah, okay, okay,
Does
okay.
that make sense? That was just there to show
Thanks.
you that. And then here, I just do my work regularly, right?
Okay, thanks.
No problem. The next one I have is this, right? So here, I want you to be able to visualize this being as given as an integral of negative. So if anything is to the power of 3 over 2, that's basically saying take the square root and cube it, or cube it and then take the square root. So I'm going to assume it this way. So I see a quadratic inside a square root. Do I see an x term in the quadratic? No, so this is already in the completed form structure. So I can carry on my substitution and kind of simplification here. So let's see how that turns out. So I'm just going to look at the quadratic inside a square root and simplify that portion first. I'm going to factor the a squared out of it. So you'll be left with 1. I'm going to take this a squared out of the square root. So this becomes a x by a whole square, right? And then I'm going to do my substitution. We know this would have been nice if this is cos of t. And the reason I'm choosing that is very specific too, right? Now, it's not going to be cos every time. It's just that this particular case I'm choosing a cos. So you would say, okay, x over a cos of t. That tells me x equals to a cos of t. Hence the dx will just be equals to minus a sine of t dt. From there, because I know I have an x squared too, I would like to write x squared as well. That will be a squared cos squared t, just for the sake of this particular question that I have an x squared. So I can put that there too. And the dx will just be that whole thing. So now we have everything together. Let's see what this simplifies to first. By this time, you already know what this is going to turn out to be. Okay, so now it's time to put everything back into the integral and do further simplification. Let's see what it turns out to be. So I'm going to take the negative 8 outside. The x squared now became this. Inside this will be a to the cube, right? Because remember, that quadratic was cubed. So it's going to be cubed. The value here will be t dt, right? Setting some of the things apart will be, this is an a squared, that's an a, that's a negative, so it will be now positive 8 outside with an a cube a cube sine cube t. That's what's going to be the bottom. You see this a cube and that a cube cancels out. This sine t will cancel one of them. So you're basically left with 8 integral cos square t divided by sine square t dt. Alright, so in this case, this will be plus 8 integral of cotangent square t. And this is where most of the people will slip, right? This integral, evaluating this little portion down there, is, for me, coming back to memory. And I'm going to Google that up, integral of what's squared. And I just need to figure out how to do that. I think this is supposed to be done using like this, okay. This needs to be converted into, I guess, the formula with the cosecant. Yes. So one odd identity that you need to remember here will be this one. So 8. This can be written as cosecant squared t minus 1 and 8 cosecant squared t you split up the integrals. So integral of cosecant squared t is minus cotangent t. So this right here will be this minus the 8 times t plus c. Okay, so I'm going to keep that here for a second so you guys can see it before I move to the next page. So we're looking at negative 8 cot t minus 8t plus c. Coming back here, t equals to, equals inverse of x over a. So when you take that thing, you plug back. Not here. You would get negative 8 cot of cos inverse x over a plus c. And that's how you solve this one. I'm gonna double check if that was the way how I originally did it before too. That was question number this one. Yeah, that was the same way. So different substitution would yield a different result, but this is how it's supposed to be, right? So Webwork does not have any trouble accepting this as it is. If it does, please let me know in Discord. I'll give you a Webwork friendly answer too, right? So give it a shot. But this should be good. Okay. Any questions about this? Is like an odd one, right? Where you would have some identities that you don't remember on top of your head. That's what you have to use. You might also go with the route which I did here. If instead of substituting as cos, you can also substitute it as a sine. If you do it as sine, then you would get a different substitution here. So all the same work in this question, when you substitute it as sine, you would get this reduced down to the opposite. To 3 sine squared over cos squared. We had cos squared over sine squared, this will be a different way, which turns into tan. Some people might be a little bit more okay. We're looking at a tan rather than looking at a cotangent. So this way also you're going to have a same result but different situations, not anything else, right? They just look different. So that was question number 5, right? We can move on to question number 6 now. Question number 6 in my version. Is 25 minus x squared, right? So here again, I'm going to do the same thing, just exact same work, just see where it goes, and going to simplify this first. So because there's no x term with a quadratic, we don't have to complete the squares in this case too. Here, okay, that's the case. The 25 comes out of this thing, becomes a 5 there, outside of square root, and you'll be left with now here I would like this to be cos. I will show you a sine way too. You know, let's try to do the sine way in this case. Let's see what happens if you were to substitute in the sine way, right? If you let x over 5 equals to sine of t, then x equals to 5 sine of t, hence dx will be equals to 5 cos of t dt, right? After simplification, this will be negative 1 over 5 dx. X squared will be just 25, no, I don't need to have a dx there, 25 sine squared t. The dx will be equals to 5 cos of t dt. And then here you would eventually square root of 1 minus sine squared t is cos squared t. Negative 1 over 5 cos t dt 25 sine squared t times cos t. This goes away with that. This 5 cancel this. Now you basically have 1 over sine squared t dt, which we know could be written as negative 1 over 25 which we just discussed. The integral is going to be negative cot of t. So negative cotangent with the negative 1 over 25 will come positive. And you know you can isolate t from here. So the final answer here will be this. How does this feel? Are you able to see the pattern that every time when you do a trig step is going to be like very very straightforward in order to kind of like get to the expression, and they flow like the way it's supposed to be, right? At some point I feel like very intimidated just because I don't know where this is going. But eventually, when you do trig sub properly, it will go in this way. And yes, I agree with this, that it will be a little bit trickier because these are not the regular cos and sine functions that people like. And but there's arguably no other way to kind of go over there. You can have them turn into a different counterparts if you choose your substitution correctly, right? If we can choose this to be, if we would have chosen this to be cos, then I would get a secant squared here. Okay, that would be case two. So it's up to you to try it out too, because you have two options. You can either substitute sine or cos here. So try either one of them, right, and see how it goes. You will see if sine is becoming ugly, then you can definitely go with the cos and try to see if that one works out better. Okay. So I think in the notes, in my notes when I made this, I would have done the other way. Yeah, I would have done the other way. So in this case, I substituted a sine, and then I got you know, this way, and I also wrote that too. It's a trouble because cosecant squared is not that common, right? So by looking at the tables, you can see like the cosecant squared is just negative cot of t, and that way you can see, an alternate approach I told you here is if you substitute x over 5 as cos, and you follow along with that substitution, this whole mumbo jumbo will now simplify to be just dt over cos squared, like it was dt over sine squared. So that is secant squared, and that one is easy, right? That one is tan t plus c, right? And t was happened to be the cos inverse of this, so you can plug it back in. So see, sometimes this substitution also works, and it doesn't really mean that it's not gonna work in the harder way too, right? So this way approach is fine too. This one's approach fine too. In homeworks, I would suggest this. On an exam, I would suggest the one that you know. Okay. The moment you see this, you should backtrack and try to go to the other way, right? And slowly you'll develop motivation towards like seeing whether you should substitute it this way or not, right? That also comes in handy. All right. We can move on to the question number 7. Oops. Question number 7 is pretty same. So here I have it this way. I'm gonna do this one silently, okay? I'm just gonna try to go this on, and then I'm gonna ask you if you can follow along and understand what I did, because that way it will make sense. Because this is like same, like what we did before too. In this case, substitution will be different. The derivative of secant t is secant t tan t. Okay, so I have it in this format here. So how about this? right? Much more smoother than the other ones, right? Because it turned out to be very good. Good stuff, right? Nice. So now I want to show you something here, which you might need it, might not need it. I would just want to show that because it's a part of the curriculum, right? When I say that, I'm going to write it in red. So when I define secant of some angle, right, this is equals to 1 over cos of an angle, right? That tells you that cos by SOHCAHTOA, right, if you remember that, is cos is adjacent over hypotenuse, right? In that example. So this would be hypotenuse over adjacent. So when you're given a secant of t as x over 10, you're given the hypotenuse and the adjacent. So if you were to draw a right angle triangle here, right, and assume that angle to be t, then the adjacent of this triangle will be 10 and the hypotenuse will be x. So this side could be found out by Pythagoras theorem to be x squared minus 100, right? So you remember that. That's okay. The answer here is asking you for 100 sine of t. And by SOHCAHTOA again, sine of t in this triangle will just be opposite over the hypotenuse. So opposite is this, minus 100, divided by hypotenuse is x. So an alternate way to write this answer would be this 1 over 100. You can just plug in the sine of t value from the triangle. And then a plus c. So these two answers are completely equivalent. Okay. This one is kind of like easy to compute for Webwork purposes, but this one's easy to compute for the examination purposes. Does this make sense? You can always reduce this expression and like substitute for this guy straight from the triangle. This is not absolutely required, but it's good to know. Okay? That's why I'm putting it out there. Good stuff. We can move on to question number 8. My version has okay. So this is a quadratic which is not in the completed square form. So we have to complete square, right? So I know how to do that. This is going to be like this. The completed square form looks like this. So an expanded form, this should look like okay. That's the expanded form of this. And I'm only looking for the A, B, and C values to convert it into, to look something nice. So let's see. If I compare this to my given quadratic here, I know by comparing these two, I can clearly say that A needs to be negative 81. Right? Because the coefficient should match up. That's why A needs to be negative 81. I also know that 2 times negative 81 times the B value must be equals to negative 108. Right? Because if you compare these two guys now, the 2AB must be equals to negative 108. So 2 times A times B must be negative 108. So that way, you'll be given the B value to be just equals to 108 divided by 162. Okay, keep that handy for a second. Now after this, the final thing to find is the C value. Whatever the constant is, AB squared plus C must be equals to 45. So you have negative 81 times 108 divided by 162 whole squared plus c equals to 45. So c is equals to 45 plus 81 times 108 divided by 162 whole squared. They're very nasty numbers. So yeah, I hate it. But let's see. They're supposed to be bad or no. Yeah, no. In the last question, I was blessed with a very easy thingy in this version, but not necessarily in this one, right? Okay, so you said C is 36, so you calculated that. The smart people. Awesome. So this is 36. How about B? Is it 108 divided by 162 still? Oh no, 9, okay. Listen to you guys. This is 9, which is good. B is 2/3, which is good. And A has to be negative 81. You can't really reduce that, right? Okay, awesome. Let's try to now carry forward our exploration with it. So let's see. We have this equation turn out to be, because it's negative in the beginning, I'm going to write the constant first, because and that'll be x plus 2 over 3. Right. I'm going to do some simplification here so that it should make absolute sense. I want to make this into a 1. So I factor out the 9. I'm making 1 minus 9. Okay, so if I factor out the 9 from the 81, this will be left with the 9, right? So now my job is to kind of cancel this. With this, we have a 3 there, and bring that in. Oopsie, no. Can't do that, just write that. So you have 9 here, and 9 here, and a square there, right? A 3 with a square. So this 9 pops out of this thing. So you have 74 divided by 3, with a dx up top. Square root of, in this case, you will see it's 1. When you bring that, let's just reduce it this way. When you expand the square, the denominator will become that number, 9, so this cancels out. So you have a rather nice expression eventually for b square root of. Right? So we have it in this form. I'm going to copy this, take it to the next page to further elaborate. So here, I would want to substitute this to be cos, So I want to substitute cos of t, so this is going to be 3x plus 2 equals to cos of t. So x is equals to minus 2/3. Hence dx will be equals to this. So now, because we've been doing this for so long, this simplifies to be just the square root understand will be just sine squared of t. The dx will just be this times dt, which eventually becomes 74 divided by 9. I'm going to bring this 3 outside here with this. This will be negative brought out sine of t divided by sine of t. So you have negative 74 over 9 and then t from here 3x plus 2. So the answer that you submit here plus c. So this was like the whole procedure, you know, where you have to start with a quadratic, you have to complete its squares, like we did here, then do the regular reduction, which is not that nice as usually, right? But it did work out fine, you know. Eventually, you just want to have 1 minus something whole squared, and you want to put that something as a trig substitution. We did that, we got the answer, right? Any questions about this? Yes, I'm going to go back to the first page. Yes, for sure.
Hi.
Mm-hmm.
I was just a little confused how you did the very last row.
This very last one, like this one.
Yeah, like how you got from the second to last one to the last row.
Oh, so from here to here, right?
Yes.
All right. So what happens here is the 64. Oh, sorry, 74, and the 9 when it came out of the square root becomes 74 over 3. Okay. And inside you'll be left with 1 minus 9 times 3x squared plus 2 divided by 3 whole squared, right? So when you expand that bracket, you have 3x plus 2 whole squared divided by 3 squared, which is 9. That 9 cancels out with this, right? So you'll be left with 74 over 3 that came from here, and 1 minus 3x plus 2 whole squared dx. Does that make sense?
Oh yeah, I totally missed that.
Right?
Yeah, that does make sense.
Yeah,
Thank
I
you.
was a little fast at that, but yeah, once you practice, you'll be able to, see that. Awesome. So we got this one true. No questions on the second page too, right? Because that's like a standard procedure now. Okay, good stuff. Now we're moving towards the end. We're looking at question number 9. Plus 8x plus 52. Right? When you have this kind of question, we know this is not necessarily a quadratic inside a square root, but we would still want to go with the trig sub route, right? So we have to compare this to the completed square form, complete the squares, do the simplification, do the trig sub, simplify, chill. That's the step. So let's see. We know I want to convert this into x plus b whole squared plus c. In the expanded form, this looks like x ax squared plus 2abx plus ab squared plus c. So comparing that to my quadratic here, x squared plus 8x plus 52, tells me that a needs to be 1, because if you compare these two, you can be like a needs to be 1. Then 2ab, 2 times 1 times b, must be equals to 8, implying that b needs to be 4. Right? So we know b is 4. Then the remainder constants needs to be the same as 52. So 1 times b squared, so a times b squared is 1 times 4 squared plus c must be equals to 52. So 16 plus c must be equals to 52. So c must be equals to 52 minus 16. And my little brain, which is the size of a peanut, tells me that should be, so I think 30, not 30, yeah, 38. No. So take away 16 from 50 gives me 36. So yeah, 38. 30, yeah, 36. That's good. You're smart. I wish I was that smart, but 36 is supposed to be the correct one, I'm guessing, okay? Even if not, then we don't really care about it. It should be fine. So now my expression in the completed square form could be written like this. 1 times the x plus b, so x plus 4 whole squared, and then a plus 36. Okay, awesome. So that's the second security that you have a calculator. It's great. So now we have it in this format. Now simplification will look something like this. You have to make this into a 1. So you're going to take the 1 over 36 out of it. You'll be left with this. X plus 4 divided by 6 plus 1. Okay? Because when you take that 36 out of it, this will be divided by 36. And 36, when combined inside the same square root, will leave you with just a 6 squared. Okay? So that's cool stuff. We got that one sorted. And now I want this inside part, in this case, to be the one that we haven't seen yet. Tan t. Okay? So when you do that as tan t, you have x plus 4 divided by 6 equals to tan t. Hence x equals to 6 tan t minus 4. So dx will be equals to 6 secant squared t dt. Okay? Keeping that handy, when you go back here, you have 1 over 36. Dx is just going to be 6 secant squared t dt. Divide by, this is going to be tan squared t plus 1. And tan squared t plus 1 is secant squared t. So the bottom is just secant squared t. And then you'll see this cancels out, this cancels out to be 1 over 6 in the event, eventually. So this is 1 over 6 integral of dt, which is going to be 1 over 6t plus c. And because t is that, you can isolate for t. T is going to be tan inverse x plus 4 divided by 6. Hence your final answer here is 1 over 6 plus c. Very smooth, right? Sometimes I believe trig sub happens to be so nice that it cancels out to just give you, an integral of dt. It happened 3 times with us, right, today in this homework, right? It's supposed to just flow like this. And trust me, it will be that easy in your head too, because I've been doing it for so long. The only difference is you only had a week to work on it, right? So there will be some differences for sure, right? You can see that, but you will gain the same foresight that I have after the consistent practice, and that's the key, right? That's the key. So that was question number 8 that was question number 9. Yes. All right. We can move on to the next one. Question number 10 is for me. And this one is also the standard trig integral, so I'm going to try to do that silently, see if you can follow along. That's the final answer. And of course, I went over silently. This does not mean that you might not have any questions. If you do, please feel free to ask. Right? Straightforward. Good. right? So we can move on to the next one, if not any more questions. Question number 11 is where I want to take a second and show you some very important facts, okay? So everybody knows that the integral of cos x is sin x, right? That's like, this is like just a basic, right? That's supposed to be this way. Now, what you don't know is what's the integral of cos squared x dx. You know? Or as a matter of fact, you can't take an integral of cos squared. Okay? Because it's just not easy to do so. So you want to reduce that cos squared into something that's a regular cos, not a power of square, right? So here we need to remember, this is the double angle or half angle formula, as people call it. Double angle or half angle formulas, people call this, and they are going to be as follows. So if you ever see a cos squared, that could be written as 1 plus cos of 2x divided by 2. So essentially, if you have a cos squared, all you do is double the angle, make that x into a 2x, and put it in this formula, 1 plus cos 2x divided by 2. So that's how you convert a cos squared. And there's also one for sine squared too, which you might need. That is the same 1 minus cos of 2x divided by 2. So this way you can reduce an expression into a regular cos and then go on with that. Okay, so our job is to make sure our integral does not have any powers of cos and it only has single powers. Okay, that's very important, keeping that in mind. Let's try to see how we can reduce this. Cos to the power 4. Some people had it as cos to the power of 6, but the rules will be exactly the same as long as you follow along with me, right? I have a cos to the power of 4, so I'm going to work with this. So cos to the power of 4 could be written as this. And the inside cos in the identity could be written as 1 plus square, right? And when you expand this, this will be equals to 1 over 4 outside. Will be 1 cos squared of 2x plus 2 cos of 2x. Right? Just like a polynomial. You want to expand this, you get that result. So we got rid of most of them, but there's still 1 cos squared 2x left, right? So I have to rewrite that one too. So this will be 1 plus this guy right here becomes twice of 2x is 4x. This plus 2 cos of 2x, right? And now if I want to write this everything in its glory by expanding everything out, this will be 1 over 4 plus 1 over 8 plus cos of 4x divided by 8 plus cos of 2x divided by 2. Does everybody follow along with how I simplified it? And these are only specific for these particular cos and sine cases. Right? I just applied a double angle formula once. I expanded the square and I happen to have another one there, so I have to apply it again. So cos of 2x became a cos of 4x, and that's how you have your simplified result here. Right? So this is how it is. So if I was to take the integral of this guy, that will be equivalent of me taking the integral of these guys. Right? Which are pretty standard, which is pretty easy. So if you take that integral here, so this could be reduced into, I think, 3 over 8. Yeah, 3 over 8, right? So 3 over 8 x plus 1 over 8 will be staying outside. The integral of cos of 4x is going to be sine of 4x divided by 4. Plus 1/2 stays outside. The integral of cos of 2x is sine of 2x divided by 2. Do you guys agree with me? That's how we're gonna formulate this, right? Any questions about how I did that integral? This was talked about in the very beginning, in the very first session we had, where we have chain rule of integration, right? If you have sine and inside there's something linear plugged in, just take the integral of cos first, and then divide by the derivative of the linear that you have. But if not, then you can also do u sub and get the same result, right? So this integral should make sense. And now my original question had to be evaluated of cos of 4 from 0 to pi. So if I want to evaluate from 0 to pi, this will be 3 pi over 8. And when you plug in sine of 4 pi and 2 pi, they're going to be 0. Okay? So rest is going to be 0 plus 0. Minus when you plug in 0, everything will be 0. So the answer to my particular version is 3 pi over 8. Yours might be different, and that's how it is. Any questions about this problem? Hopefully, no, right? Okay, everybody's okay with that. Perfect. That brings us to the last problem of this Webwork, which is going to be problem 12. So problem 12 is coming back to the integration by trig substitution, right? I'm gonna give it a silent treatment. Let's see if you guys can follow along. Any questions regarding up to this spot? Okay, we're good so far, which is good. And then now here you have a tan squared of t, and this is where you have to use the identity to convert it into secant. So integral of secant squared is going to be tan minus 5t plus c, and t is equals to secant inverse of x over 5. So we get that, and this will eventually reduce to 5 tan secant of x over 5 minus 5 times secant inverse of x over 5 plus c. So right now it looks very hideous, and I want to try to use the SOHCAHTOA method to kind of reduce it into something nice, right? So in a SOHCAHTOA, secant, okay, is just 1 over cos, and cos is adjacent over hypotenuse, so this is going to be hypotenuse over adjacent, right? So in a triangle, has this angle t, the hypotenuse is going to be x, the adjacent is going to be 5. So this is going to be x squared minus 25. That's what it is. And I am looking for tan of that number, okay? Tan from here will just be 5 times tan is this divided by that. Opposite over adjacent, right? So square root of x squared minus 25 divided by 5. That cancels out. Minus 5 times, you can't really do anything about t, you know. You can write it nicely in other forms, but might as well just keep it in the secant inverse. X over 5 plus c. So that's like one extra step, but not required at all. I'm pretty sure you guys can follow along like what's going on in this extra triangular way of writing things, but it's just an extra thing, nothing special, right? And with that, I think we've done all the 12 questions that we had in this Webwork. Hopefully it makes sense now a little bit, right? I think having this walkthrough would benefit. There are 2 ways to think about it. I see like there's me depriving you of the hard work and the hustle you have to put in to understand this. That's one side of it, and the other side is I'm trying to help you at least understand it, right? So the benefits will outweigh the damage, right? I can't leave you guys to just be okay with not learning it properly and then struggling later on. You saw that happening in the midterm. The reason why midterm was apparently hard is because the math department does not enforce a lot of strong and like strict practice habits, and we just want to make sure that you guys have that kind of thing. So telling you that this is how it's supposed to be done is kind of partially helping you learn as well. And the motivation behind me going through every single question here and not just simply giving you this PDF that I have already worked on, for every question in this Webwork, and I have that for every Webwork too. So the reason why I'm not handing this over to you and manually showing you how I got that 3 pi over 10 instead of just sending you these solutions is because I do not promote academic dishonesty. This is a very good place to where we talk and discuss things, and we make sure that we do. But we're not many people, but it's good, enough that we have those many people putting effort. And I'm pretty sure as the weekend comes by, you'll see more and more people want to be, doing most of this. But can't control everybody. Just try to provide an opportunity to most of you guys. But that's just how it is, right? So we're done with all the questions. If you have any more, I'm more than happy to stay back and answer those. So I'm gonna